All right, can you hear me? Good evening. Thank you all for coming. My name is Tomas Kriska. I'm currently serving as president of the Milwaukee Astronomical Society. We have a special night with a special guest. So special that we have to schedule an extra meeting, because we normally don't have meetings during the summer months. So what makes this night special is that our former club member, Fanson, who became a very successful professional astronomer, has accepted our invitation to talk about his work. Jim grew up in Waukesha and became interested in astronomy at an early age. As he grew older, he joined the MES and was attending meetings. He participated in construction of our biggest dome and also designed the big fork for the club's 26-inch Cassegrain telescope as an engineering project for school in the early 1980s, I believe. After earning his bachelor's degree in engineering mechanics at the University of Wisconsin-Madison, Jim moved to California, where he earned a PhD degree in applied mechanics at the California Institute of Technology. After the grad school, Jim joined the NASA's Jet Propulsion Laboratory in 1986, specializing in space telescopes. He was a member of the team that fixed the Hubble Space Telescope's blurred vision in 1993 and served as lead engineer for the design of Spitzer Space Telescope. He also served, among others, as project manager for our Galaxy Evolution Explorer and Kepler space telescopes before becoming the project manager for the Giant Magellan Telescope. The GMT will be a member of the next generation of giant ground-based telescopes that promises to revolutionize our view and understanding of the universe. So please join me in welcoming our tonight's guest, Dr. Jim Fanson.
Thank you, Tomas, for that generous introduction. And I'm astounded that so many people have turned out. And I'm in your debt. Thank you very much for coming out this evening. It's a tremendous pleasure for me to come back to this observatory. I grew up a short bicycle ride from here, and I joined the NAS when I was in grade school. And it was really what spurred my interest in astronomy. And the telescopes have, as you heard, essentially been my career since leaving Wisconsin. So some of my colleagues and friends from that era, we're talking about the 1970s up till 1980, are here, so thank you for coming out. It really warms my heart to be here. I have to say, though, that it's so posh in here compared to what I was a member. It had a very military feeling back in that day. And I can remember spending many very freezing cold nights out here observing and developing film in the dark room, such as it was back in those days, and having all the beautifully manufactured star charts. It was a very hands-on experience, and it was a lot of fun. So I'm going to talk to you a bit about the Giant Magellan Telescope. And I am not a card-carrying astronomer. I'm not a scientist. I'm an engineer. So I'm going to give you an engineer's perspective on the telescope, and I'll try to answer as many questions as I can. But before I do that, I do want to just show you a little bit of what I did when I was a member here. So I actually made these drawings that were used in the fundraising for the observatory. And as was mentioned, this orange fork mount I did as a design project as a senior in college. So I rummaged through my files to find these old drawings. And here I am. You have these posted on your webpage. This is what I looked like when I was a young man, and we did many crazy things to build the observatory. We did not have the hubris to think that we could actually lay the block, so we hired professional masons to lay the block. As I recall, they were paid in beer.
Beer and
A little bit of cash. All right, so I'm going to talk a little bit about the scientific motivation for the telescope. You're all telescope people, so I don't need to dwell on that. I'll talk a little bit about the partnership that's behind this project, and I'll give you a status report on our design and construction, and then answer questions. I want to start out by talking about the history of telescopes, which has really been a quest for size. And what this plot does is plot the aperture of the world's largest telescope as a function of time. Back from the 1600s, when Galileo first turned a telescope to the heavens, up until the present time. And if you plot it on a log scale, you can pretty much fit a line through this trend and determine that telescopes double in size roughly every 30 years. And the last generation of 8 and 10 meter telescopes that was developed in the 1980s and 90s, it's come time now for telescopes in the 25, 30, 35 meter range. So it's really time for the GMT and for the other extremely large telescopes that are coming along. And when you look at scientifically, these telescopes enabled the early telescopes, of course, that were small aperture, were really focused on the solar system. Galileo discovered sunspots on the sun. He discovered mountains and craters on the moon. He discovered the moons of Jupiter. They really revolutionized our understanding of the solar system. Then later on, the study of the galaxy, the understanding that, in fact, the galaxy has a shape and where our location is, the size of the galaxy. Then when you get into the 20th century, you're talking about the 100-inch telescope, the 200-inch telescope. They were really directed extragalactically to determine the expansion of the universe, the fact that there are island universes, which we now call galaxies, of which the Milky Way is only one. And again, our sense of scale of the universe was revolutionized. And the current generation of telescopes is really now beginning to lead to new physics, the dark matter, the dark energy, the multi-messenger science with the detection of gravity waves from in-spiraling binaries and other massive objects. And so we're looking forward in the future with the extremely large telescopes to be not only making progress on questions that we know how to ask today, but by introducing new discovery and questions we don't yet even know how to pose today. One of the things that we're looking forward to, now that we have an understanding of the prevalence of exoplanets orbiting other stars, is to go beyond the detection phase of these exoplanets and begin to characterize them, characterize their atmospheres, look for signatures of biology on planets that might be in the habitable zone. So it's really a wide open frontier. I want to say that it's really aperture that drives discovery. Of course, telescopes can be built for very special purposes. The Kepler telescope, space telescope, was built specifically to find transits of exoplanets. But by and large, aperture is what enables discovery. One of the key metrics in astronomy and observational astronomy is the sensitivity of the telescope and the device you're using to make measurements. And the sensitivity is essentially the ratio of the collecting area of the telescope to the size of the image that you're concentrating the light in. And as we know, the collecting area goes as the square of the diameter, and because of lambda over d physics of light, the size of the image is inversely proportional to the diameter, so the area of the image, again, goes inversely proportional to the diameter squared. So this ratio really scales as diameter to the fourth power. So in terms of sensitivity, there's an enormous advantage in large telescopes, particularly if you're working at the diffraction limit. And of course, for ground-based telescopes, the atmosphere has something to say about that, and I'll talk about that for GMT. So just to give you a couple of ideas of what a telescope in the 25-meter range will do for you, this is an image of the galactic center. The X marks the spot of the supermassive black hole at the center of our galaxy. This is an image using adaptive optics to combat and defeat the blurring effects of the atmosphere. It's 1 arcsecond on the side. In this frame, and what you're seeing are the various stars that are in the vicinity of the galactic center. And if we were to do an image at the diffraction limit with GMT, this is the kind of resolution that we would get. Sagittarius A again is the location of the supermassive black hole. So there's just an enormous benefit in going to a larger size. So the history of the telescope is really a history of what is the largest telescope you can afford and what's the largest telescope your technology will enable. Here's another example. This is a simulation of a galaxy at a Z of 2, so this is like 80% of the way back to the Big Bang. On the right, you see a simulation of what the Gemini 8-meter telescope with adaptive optics would show you. And if we transition that to what the GMT would provide, you can see, of course, now you can begin to study the subregions within the galaxy and understand what's going on in the physics of these objects. One last thing I'll show you. This is a plot for exoplanets. The stellar type or stellar temperature is on the ordinate on the left. And along the horizontal axis is the rotation period or the orbital period of an exoplanet in days. You can see up here in the right-hand corner, this is the Earth, 365-day orbital period, and it's orbiting a G-type star. These are cooler stars, which are more prevalent in the galaxy. And if you do a computation of how far you have to be from the star for the temperature to enable liquid water at the distance of a planet, you can define this region called the habitable zone. This is where we would look for planets that could potentially support life. There's a spacecraft that was launched about a year ago called TESS that is doing for the local brightest stars what Kepler did for a collection of 150,000 stars, looking for exoplanets around the nearest stars to our solar system. And this indicates the sensitivity for detection of planets in this domain. Another method for finding planets is the radial velocity technique, where you measure the Doppler shift of the star and the reflex motion due to the gravity of an orbiting planet. And the state of the art today for sensitivity is about 50 centimeters per second. And what we're building in our first generation instrument, which we call the GCLEF, will give us 8 centimeters per second resolution, enough to begin to detect the reflex motion of Earth-like planets orbiting in the habitable zone around Sun-like stars. So there's just an enormous degree of excitement here about what we can do in exoplanets. Okay, I'm going to stop talking about the science motivation, but I will point you to our webpage where you can download the current revised version of our science book. And the science book is written so that you can glean understanding regardless of the degree of expertise you have in astronomy. So beginners can derive something from this science book, as well as professional astronomers. And it has chapters that are devoted to basically every part of the domains of astronomy, from stars, galaxies, dark matter, the early universe, galaxy formation, galaxy evolution, and so on. So you can download the science book and have fun with it. Okay, I'm going to talk now a little bit about the consortium that's behind the GMT. So GMT is a privately funded scientific project. Our founder institutions are mainly scientific organizations or universities that have an interest in doing research in astronomy and would like access to the world's largest telescope. Most of our founder institutions are in the United States. We have foreign partners in Australia, South Korea, and Sao Paulo, Brazil. So you can see we are well represented scientifically. We have the University of Chicago, Harvard, the Smithsonian, the Carnegie Institution for Science, Texas A&M, University of Texas, University of Arizona, and Arizona State University in the U.S. So we have really a powerhouse of scientific institutions behind us. In our collaboration, these institutions provide cash to GMTO, or the corporation that they have founded. which I'm an employee of. And then at GMTO, we have formed a project organization to implement the project, to design, build, and operate the telescope. We're going to be locating the telescope at Las Campanas in Chile. This is at the very southern end of the Atacama Desert. It's in a tract of 100 square miles of property purchased by the Carnegie Institution in the 1960s. And it's a very superior site. It's at a comfortable altitude. It's a little over 8,000 feet, so you can actually live and work at that altitude. It's very dry, and the airflow is very smooth, and the temperature fluctuations are very moderate. So it's an exceptional observing site. And I have to say that I think in the next 20 to 30 years, the majority of astronomy infrastructure is going to be in Chile because of the superior conditions. There are really three conditions you're looking for to site a telescope. You want a place that's dark, an optical telescope. You want a place that's dark. You want a place that's dry so that moisture doesn't absorb light. And you want a site where the airflow is very smooth and the temperature is very uniform, so you minimize the effect of the atmosphere on optical distortion. And this site is superior in all three of those categories. The nearest city is La Serena, which is about a 2-hour drive. And I'm not going to say more about it than that, unless there are questions later. This is a artist rendering of what the completed observatory would look like at Las Campanas. The mountain was leveled several years ago, and we leveled it so that we could place not only the Giant Magellan Telescope, but have another area on the other side of the mesa for a second large telescope sometime in the future. The building next to the what we call the enclosure is this large rotating building that protects the telescope during the daytime from the elements. The building next to the enclosure is devoted to recoating primary mirrors to keep the reflective coatings efficient. And then to the edge of the mesa, we have what we call a utility building for all of the noisy machinery. The pumps that pump hydrostatic oil, coolants, and so on. So they'll be vibration isolated, and we're doing what we can to minimize vibration into the telescope. And then down here is our water storage, treatment and distribution system, and we have some temporary offices. We find that people have a hard time seeing, getting a sense of scale. So we work in Pasadena, so we moved the telescope to the Rose Bowl, so you can get an idea of what the scale of this thing used to be. So one of the things you notice about our telescope that's different than, let's say, the Keck telescopes that were built a couple decades back, or the other two extremely large telescopes that are being developed, is that rather than build our primary mirror out of relatively small hexagonal mirror segments and then put them edge to edge, we're using a different approach. We're using large circular mirrors that are manufactured at the University of Arizona, and we're going to form a primary mirror out of 7 of these segments. So 6 of them are identical on the outer ring, and then there's a central axisymmetric segment. And the technology required to phase these segments so that they form and act as though they're part of a single mirror is new. Nothing like this has really been tried before. So there are advantages associated with using fewer, larger mirrors, but there are also some technical challenges. So if we look at the telescope itself, one of the things that distinguishes us is that the design of GMT, like the design of the 6.5-meter Magellan telescopes that are currently operating at Las Campanas, is that we have an optical design called an aplanatic Gregorian design. These are much less common. Typically, you would find a Ritchie-Chrétien type of design. One of the advantages of such a design is that we get a real focus of the primary mirror in front of the secondary mirror. So this is where we can put a lot of calibration equipment and actually access a focus. Because the secondary mirror is behind that focal point, the secondary mirror is concave. And the Ritchie-Chrétien secondary mirrors are convex, which are a bit more difficult to manufacture. Another advantage that we have is we get a very wide field of view that can be well corrected with a corrector plate. And we get a very compact plate scale. So at the focal surface, the scale is about 1 arcsecond per millimeter. And what this allows is for our scientific instruments to be much more compact. So they can be of higher quality, they can be less expensive, easier to develop, and we now have the ability to place the instruments on the telescope so that during the night, as we want to move from one type of observation to another, depending on the weather, or depending upon targets of opportunity, we can rapidly switch from one instrument to another. Let me move on here. I'm now going to show you a video. This is on our website, so maybe some of you have seen this, but this is, we'll sort of do a fly through the telescope, and I'll try to narrate this as we go along. I'll point out that the enclosure in this old animation is a little different than the current design, but you can ignore that. So as we approach the telescope, the bipartite shutters of the enclosure open up, and you can see the telescope slowing down on the elevation axis. The covers that protect the primary mirrors are retracted, revealing the reflective surface. These red-colored objects are the mirror cells that the mirrors are supported in and controlled. This is a conventional mount, meaning that it has an azimuth degree of freedom, that's the horizontal degree of freedom, and then there's an elevation axis. These are hydrostatic bearings, so they float on a thin film of oil. This is a technique that was developed for the Palomar telescope. And then at the heart of the telescope, in the mount, is what we call the Gregorian instrument rotator, where all of our scientific instruments are mounted, as well as our acquisition guide and wavefront sensing system. So these are instruments mounted on the top of this 6 by 9 meter Gregorian instrument rotator. And then we have more instruments that are located in the body of the 6 by 9 meter cylinder. We don't show the instruments in here, but they're located in this volume. So most of our scientific instruments are at the core of the telescope mount, which is also very unusual in telescope design. Surrounding the telescope, as I mentioned, the enclosure protects the telescope in the daytime, but at night when we're observing, we really prefer that the enclosure disappear entirely, because all the enclosure can really do is release heat or absorb heat, cause temperature gradients in the air column that the telescope must observe through. And so the best we can do is just to well ventilate the enclosure and open up a lot of apertures to allow the air to flow through. So this is the primary mirror. It consists of these 7 segments. Each of these segments is 8.4 meters in diameter. So each of these mirrors are the largest mirrors in the world. And they're manufactured using a unique technology at the University of Arizona. And I'll show you a video, a time-lapse video, of how these mirrors are made. And I'd like to point out that for most of my career, I was involved in building space telescopes. The advantage of space telescopes is that they're above the atmosphere, so you don't have to worry about the atmosphere. There are a lot of advantages that come from that. The Hubble Space Telescope has done, continues to do fantastic work. But when you put something in space, it means you have to place it on a rocket, and that means that the size of the telescope is necessarily limited. So just to give you a sense of scale, I'd like to point out that the hole here in the center of our center segment, where the light comes through to reach the scientific instruments, that is the same size as the mirror in the Hubble Space Telescope. It's 2.4 meters in diameter. So the Hubble, by ground-based telescope standards, the Hubble is really quite small. And even the James Webb Space Telescope that NASA will be launching in the next couple of years is small by comparison to ground-based telescopes. So there are things that are best done in space, and there are things that are best done on the ground, and you really need both types of machines to be able to address the questions at the frontiers of science. So I'm now going to narrate this time lapse. This is underneath the football stadium at the University of Arizona. This is the furnace in which the mirrors are made. So you can see the walls of the furnace with the Inconel bars that provide support being built up. And then the mold for casting the mirror is machined out of material that's much like the tiles on the space shuttle. We then put glass in by hand in small pieces, put the lid on the furnace, heat it up, and spin it, and flow the glass into the mold. You can see here the glass melting and then flowing into the interstices in the cells. And then when we open up the furnace, we have a completed mirror with a parabolic surface on the top due to the centrifugal force of having spun the mirror. So this is what they look like when they come out of the furnace. They're then lifted, rotated, and all of the refractory material that was used for the mold is cleaned out. And what you then have is a monolithic piece of glass that's light-weighted, that has thin cross-sections so that you can get the heat can come out very quickly and uniformly, and we can support the mirror without as much weight as you would have if it were a solid piece of glass. So because these mirrors are cast, you cannot manufacture them out of a zero thermal expansion material. So we use a material that's much like Pyrex. It's a little higher quality than Pyrex. So it's a low expansion material, but it's not zero expansion. So this means that we have to be very aggressive about controlling the temperature of the glass of these mirrors. And I'll say a little bit more about that in the next slides. This is a panoramic picture I took in the mirror lab. Again, this is underneath the football stadium at the University of Arizona. This is what we call the polishing hall, and what you see in the foreground is the polishing machine that is used to polish these large mirrors. In the background, you can see another mirror blank. That's the grinding machine that does the forming or generation of the surface and does the rough grinding. And in the center, in between these two stations, is an optical test tower where we actually are able to measure interferometrically and by other means what the figure of the mirror is, what the shape of the glass is. And we use that to determine what material should be removed on the next cycle of polishing. So we polish for a while on the polishing machine, we go into the optical test tower, we measure the surface, generate a heat map, we come back and polish some more, and then converge down to a surface which will have the accuracy of about 25 nanometers, or about 1/millionth of an inch RMS. So if you can imagine taking this 8.4 meter mirror and stretching it out to be the size of the continent of the United States, the largest peak to valley variation would be about 1/2 inch. So it's a very, very smooth surface, which is, of course, what you need for an optical telescope. There was a question as to whether or not the mirror lab could manufacture an 8.4 meter off-axis mirror segment. And so a lot of effort was put into actually manufacturing the first mirror segment. That was successfully completed. And what you're seeing here is the first mirror segment in its transport container being placed in storage at an aircraft hangar near the Tucson airport. We just finished the second segment. Here you see it being lifted. They put a protective coating on the front surface and then lift it with essentially a large number of suction cups. And it's being placed in its transport container. And just last week, this mirror segment was placed next to the first one in the hangar near the airport in Tucson. This is mirror segment 3. So this is finished its surface generation and rough grinding and is now being placed in the polishing machine. And I should say that the second mirror that was polished, the second off-axis mirror, was done much more rapidly than the first one. So the team at the University of Arizona has learned enormously about how to efficiently remove glass to converge on the desired shape. The fourth segment, which is the center segment, which has the hole in the middle, is ready for front surface generation. You can see this mirror is still in the furnace, the rotating furnace. And what they're doing here is cleaning the surface of debris and looking for trapped air bubbles or other inclusions. There's quite a bit of material that's removed off the front surface, and we discover that once we're finished grinding and polishing, there are very few, if any, defects in the glass. They're really very high-quality castings. This is mirror segment 5, and this is showing you the back surface. So this is where all of the hexagonal light-weighting parts of the mold were placed. and behind each of them then is an aperture, so you can see the hole in the back. And this is where we place our control support hardware for supporting the mirror. And I wanted to tell you a little bit about how we go about supporting and handling the mirrors. So the telescope, the concept for the design is that the mirrors rest in these mirror segments, and every once in a while we're going to need to put a fresh reflective coating on each of these mirror segments. And so we have a bridge crane at the top of the enclosure, and we will do a lift of these mirror cells, lower them through an aperture in the observing floor, and then out to the coating building next door, and then we'll reverse the process. So during the 50-year lifetime of the observatory, we're going to do several critical lifts like this. So we were thinking to ourselves, who should we talk to understand how to specify the overhead cranes and do the training and procedures. We went down to the Kennedy Space Center at NASA and talked to the crane operators that lift the space shuttle components in the vehicle assembly building. They have a perfect record over 4 or 5 decades of doing critical lifts, and we learned quite a bit from them about how to go about approaching this task. The mirror segments involve, we start the mirrors with about 20 tons of glass when we do the casting, and we remove about 3 tons in the grinding and polishing, so you're left with about 17 tons or so of glass. We have about 23 tons of steel. The mirror cells are about 10 meters wide and 3.2 meters high, so you can actually stand vertically inside one of the mirror cells to work on the back of the mirror segment. This might be getting a little technical for you, but if you're curious as to how we support and control these mirrors, what I have here is a diagram that shows the back of the mirror. This is the glass on the back surface, and we bond using an RTV rubber, what we call pucks, and the weight of the mirror is supported on these pucks, and the load is then transferred to what we call load spreaders. These are metallic frames, triangular or rectangular in geometry. And then attached is what we call a support actuator or force actuator. And what we do is pneumatically control the amount of force that is placed at this point. So as the mirrors are moved around and the gravity angle changes, which wants to distort the glass, we know how much force to put on the back of the mirror in order to maintain the surface in the exact shape that we want. In addition, we monitor starlight continuously, and we adjust the shape of the mirror every 30 seconds. So we are constantly controlling the front surface of the mirrors, and every 30 seconds we make an adjustment. When the mirrors are not in use, or if there's an earthquake that should occur, and I'll talk to you a little bit more about earthquakes in Chile, we have what we call static supports, which are basically like springs. They're made out of wire rope. They're like wire rope baskets. And we place them on the top of the mirror cell weldment with a clearance, both radially and axially, so that if we experience an earthquake, which would very quickly overcome these pneumatic actuators, the mirror is captured by these static supports and protected and cushioned against the seismic acceleration. So on the back of a mirror, we have all of these red load spreaders, and the load spreaders, again, transfer the load from where we were bonding onto the glass to the actuators. So we have about 165 of these pneumatic actuators behind each mirror segment, and about 326 static supports. In addition to these, we have 6 what we call heart point actuators that are used to define the 6 degree of freedom, X, Y, Z, and 3 rotations. So exactly the orientation of each of the mirrors in space. And then we have a thermal control system. We move a lot of air through the back lightweighted cavities of the glass in order to keep the temperature very uniform so that we don't get thermal distortions that we have to then bend out of the glass. We're in the process now of finalizing the design of the control system for the primary mirror, and we're going to test it all out in what we call a test cell. So this is my test cell team, and you can see this weldment that they're sitting inside of. This is a weldment for the primary mirror, not as tall as the production mirror cells, but this will fit underneath the optical test tower at the University of Arizona. So our plan is to populate this with all of the control actuators and thermal control equipment. Start out with a metallic simulator of our primary mirror, verify that we can control it the way we need to control it, tilt it to gravity, so we put it in different orientations, and then remove the metallic mirror simulator. We'll put one of our completed glass segments and put it under the optical test tower, and we'll verify that we can actually control the figure of the mirror to 25 nanometers RMS to the desired figure. Coming to the telescope mount, this shows you what the mount looks like. You can see a human figure again here for scale, and it shows you we have a telescope structure which has the usual azimuth and elevation degrees of freedom, but then we have this Gregorian instrument rotator I mentioned during the video, where all of our scientific instruments are located. And the reason you need something like this is that when you track an object on the sky with an L-azimuth mount, they're not like these equatorial mounts that you have here. They're more like a Dobsonian mount. The image will rotate as you're tracking an object. And so you need to de-rotate that if you're going to take long time exposures with scientific instruments. The way we do that is to introduce this third degree of freedom. So this whole cylinder is basically rotated to de-rotate the image motion that occurs from tracking an object. So we have a large steel mount that's a precision mechanism with 3 degrees of freedom. We've gone through a 2-year procurement process and are now negotiating a contract with the bidder that we've selected. I'm not at liberty to tell you who that is, but we'll do a press release when we have the contract completed. I mentioned one of our challenges is how do we phase these segments so that they behave as though they're a single 25-meter telescope. And one part of that story involves interfering light from adjacent edges between segments. So each of these is an area where we interfere light from one segment or another, either side of the gap between the segments. And then this forms an interference fringe pattern, which we then pass through a prism to disperse the fringe. So the fringes that you get from one of these measurements is dispersed in wavelength, and then if you have a piston motion between the two segments, it affects the fringes differently depending on the wavelength, and it causes the fringes to tilt. And by measuring that tilt, we can tell exactly what the piston phase area is, and then we can command the mirrors back into the proper phase. So this is what we do continuously using starlight from guide stars. This is accomplished with what we call our acquisition guide and wavefront sensing system, and you can see a diagram of one of these in the center pane. And again, mounted to the top of this Gregorian instrument rotator, there are 4 of these assemblies, and they have arms that reach out into the field of view, into the focal surface, and they pick off light. They can patrol in here for a guide star, and then they pick off light of a guide star, and we use that to do the interference measurements. We have a phasing camera in here, which we've been prototyping up at the 6.5 meter Magellan telescopes at Las Campanas in order to verify that the wavefront sensing actually works in practice the way we think it should work in theory. So we periodically go out to the Magellan telescopes to do these measurements, and we've been testing out these dispersive fringe sensors in the prism array. You can see the prism array here. There's one of these hexagonal prism elements for each of the pairs of mirror edges that we interfere. Now we come to the secondary mirror. And you will have noticed from the earlier figure that the secondary mirror is also segmented. So we have a doubly segmented optical system, which you might at first think is a nightmare thing to try to align. We have a way that we believe will make the alignment straightforward. But the interesting thing at the secondary mirror is this is where we're going to do our adaptive optics. So most telescopes do adaptive optics in what's called a post-focal scheme, where you take light through the telescope, you take it out the side, and then you go onto an optical bench and you have a lot of deformable mirrors and wavefront sensors. But by doing that, you are losing efficiency because you lose light at every optical surface, every reflection, every lens, you lose a bit of light. So what we're going to do is put adaptive mirrors up at the secondary. So each of these 1 meter diameter secondary mirror segments will be essentially an adaptive optic. So you can see a photograph on the left of a prototype adaptive secondary mirror. The way these work is that we build a thin shell of glass, typically 2 or 3 millimeters thick, so that it's quite flexible. And then we bond onto the back of that membrane these magnetic targets, and they are matched to electromagnetic actuators in a reference body, which has a very stable shape. We then energize the actuators and we float this 2 to 3 millimeter thick glass surface, which has a reflective coating on it. We float that in a magnetic field, and then at very high bandwidth, meaning 1 or 2,000 times a second, we can bend that glass into a shape to compensate for the distortion being caused by the Earth's atmosphere. So across all 7 of these segments, we'll have almost 5,000 actuators that we can operate at high bandwidth to correct the atmospheric distortion. And by doing this up at the secondary mirror, it allows us to do adaptive optics correction over a wide field of view of the telescope. So we have a number of different observing modes. Let me skip to the observing modes. So this is too busy to actually read, but we have different ways of correcting for atmospheric distortion. The first option is we don't do any correction at all. We just look at we just try not to make it worse than what the atmosphere does. But then these other methods use various techniques to correct for the lower ground layer of distortion across a wide field of view, or if we're trying to do something like image an exoplanet, we use a different method to do the maximum correction over a narrow field of view. So you've all experienced this effect of the atmosphere that you can see illustrated in this picture of this mirage on the asphalt surface. So what's going on here is as the temperature of the air changes, its refractive indexes change. And typically in the atmosphere, you have these cells of air that each cell has a slightly different temperature, and the turbulence in the atmosphere is moving the cells around. And as the light comes through the atmosphere, it gets diffracted around into this zigzag path, and that's what causes stars to twinkle when you look at them with the naked eye. So it's this distortion that we're measuring, and then we bend the adaptive optics into a shape to correct that millisecond by millisecond. So that's the concept.
You're doing that off of guide stars?
That's done off of guide stars. And in the case where we're looking at a part of the sky where there are not bright stars to use as guide stars, we will propagate lasers to excite the sodium layer in the atmosphere that's left behind by meteors that burn up in the atmosphere. And that'll form an artificial guide star we can use for this. So I mentioned that the optical design we have allows our instruments to be very compact. So we've actually defined 11 different locations on the telescope where we can put the scientific instrument. And on the right-hand side, you can see these what we call direct Gregorian instruments. These are in the body of the 6 by 9 meter Gregorian instrument rotator. And then these are the instruments that are bolted on the top that you saw in the video. One instrument is at what we call the gravity invariant station, and this is mounted to the azimuth disk as the telescope rotates, so the gravity vector is always in the same orientation. And this is where we're going to place the Shell spectrograph that we're going to use to characterize the atmospheres of extrasolar planets. This is where we're going to try to get the 7 centimeter per second radial velocity precision. So we need a very stable location for that. So it's going on at this location. And then it's fiber coupled up into the focal surface. Because we're interested in really the physics of what's going on with these objects, most of our scientific instruments are spectrographs, either in the optical or the infrared. And we will build an imaging camera that will be used for commissioning the telescope and to generate beautiful images to go on the front page of the New York Times. But most of the physics is derived from the spectrographic instruments. So I want to talk about another one of the challenges. We touched on it earlier, which is, unfortunately, Chile is a very seismically active part of the Earth. And this is a plot that's taken from the seismic analysis, and it shows the coastline of Chile and various earthquakes. And you can't quite read the magnitudes here, but they're typically in the 8s. Here's an 8.8. And in fact, the strongest earthquake ever measured on the Earth was the magnitude 9.5 that occurred off the coast of Chile in 1960. This is the earthquake that generated a tsunami that actually killed people in Hilo Bay in Hawaii. So you get very strong, very powerful earthquakes in Chile. And for a telescope of this size, we have to do something to protect the telescope against these events, or we're going to have catastrophic damage with these large glass mirrors. So what we have done is to define earthquake magnitude at various levels, including what we call a survival level earthquake, that we use to design against and to do analysis to quantify what kind of risk we're taking with the observatory over its 50-year lifetime. So what we've decided to do to protect the telescope is something that's never been done before, and that is to place seismic isolators into the pier, the concrete pier that supports the telescope. So this is a cross-section drawing that shows the telescope up here, and this is the azimuth bearing that rests on a concrete pier, so you can see the cross-section of the concrete ring wall. And down at this station, we're going to break the concrete ring wall and place 24 what are called single friction pendulum seismic isolators. So these are devices that are illustrated in the figure here. You have a plate that's attached to the lower part of the pier, which has a concave surface, and then there's a piece that slides along this concave surface that forms a pivot or a fulcrum for another plate that is affixed to the upper part of the pier. And what this does is it allows the ground to move laterally and allows the telescope to remain relatively stable, so that the pier can slide as the ground moves, and that force is not transmitted to the telescope. So by placing 24 of these devices in the ring wall, we can drastically reduce the amount of force that is reacted to the telescope. Yes, sir?
What if the ground opens up?
If the ground opens up and swallows the observatory, then we have a bad day.
Okay.
But typically what's going on in Chile is it's a seismic subduction zone. So there's a tectonic plate in the Pacific that is subducting below the continental plate. And so the earthquakes tend to be quite deep, many kilometers down underground. And so you typically don't get something that opens up on the surface, but you get a lot of motion of the ground due to the elastic waves that propagate through the plate. So it turns out that these are commercial products that are used commonly in civil engineering to protect buildings, bridges, and other things. And I noticed that when I went to the California Science Center, which is near the USC campus, they have one of the remaining space shuttle orbiters, the Endeavour, and they have it on display, and you can see the bottom of the space shuttle in the upper part of this image. But I just draw your attention to the blue object. This is a friction pendulum seismic isolator, and the orbiter is resting on 4 of these. So California, Southern California, is another seismically active area. They don't want to drop the space shuttle on the floor, so they actually have it seismically isolated. And then the other thing I discovered, in the city of Pasadena, there's this beautiful, early 20th century city hall building that had been badly damaged by earthquakes over the decades since it was built. And they underwent a large conservation effort where they excavated a new foundation for the City Hall building complex. And this whole building complex is now floated on 240 of these single friction pendulum isolators. And when you crawl underneath the City Hall, as I did to take this picture, you can actually see one of these isolators would be very similar to what we have in mind for the GMT. The atmosphere is another thing that we have to design for to minimize the adverse impact. So what we've done is we're working with Boeing Company, and now we have our own in-house computational fluid dynamics capability so that we can model the effect of the atmosphere and understand the heat transfer. So what kind of heat is released into the airflow, and what does that do to the refractive index of the air, and what does that do to the optical distortion of the light that's passing through that air column? What does it look like in the focal plane? So we did a study that helped inform how we were going to design the enclosure. And you can see that there are 3 different concepts. The concept in the upper right basically has a solid ring wall for the enclosure. In the lower right, it's very open to allow the air to flow unimpeded underneath the observing floor and underneath the telescope. And here is a hybrid version. And what is plotted in color is the gradient of the refractive index of the air. So the rate of change of the refractive index. So you can see that there's a lot of gradient near the surface because the ground heats the air, and so you have this heated ground layer. And the fear was always that if you put an obstacle against the airflow, you get a stagnation vortex that forms at that obstacle, and then you can uplift air over that into the enclosure and into the column that the telescope observes through. So the initial concept was we were going to have it very open, but then this is very difficult to get something that is strong against a major earthquake. So we did enough analysis to convince ourselves that the scale of our observatory is such that even though we form a vortex, it's not high enough to influence the flow into the observatory. So we've used these techniques to help us understand how to design the enclosure, its ventilation system. It turns out that sharp corners are a problem. So in the artist rendering, you notice that many of the corners are rounded. So we try to eliminate local effects like this. So what we're trying to do is to minimize the damage to the image quality that's caused by the airflow across the observatory. I'm now going to show you the status of the construction. This is the peak at the Las Campanas Observatory where we are building the observatory. The flat part of the mountain at the top is where we're going to place the telescope. And then down on the flanks of the mountain, we have 2 what we call support areas. This one at the bottom is our residence area, so we've built our dormitory structures, our dining facility, our recreation facility. So we have a building for the construction crew and a building for our own staff. And then we have a technical support area, which has been graded now, but has not been being used. And that's where we'll have backup generators, heat exchangers for fluids that have to be cooled, that we bring down from the telescope down to this area. So we actively collect heat off of the telescope and release that heat downwind away from the observatory. So the prevailing wind direction at this site is from from in the screen toward you. So by releasing heat in this area down below the peak, that air, warm air, can be carried away without impacting the observing of the telescope. This is what the site looks like around sunset. And you can see in this image, we have some temporary offices on the summit. This is the excavation that we've now completed for the foundations of the observatory. This is a smaller excavation for the coating chamber that will be used to coat the primary mirrors. Part of that chamber will be subterranean, so we can roll the mirrors into the chamber conveniently. We have built two 50-meter towers. You can see one of them here in this image. So we did scintillometer measurements to measure the turbulence profile of the airflow in the first 50 meters above ground level. And then we're doing other measurements of wind speed and air turbulence.
Do those stay there?
Excuse me?
Do those stay there after the telescope is up?
So will they stay there? Our concept is to leave one of them there, possibly take the upper portion of it down, but leave a mass dim, that is seeing measurement device, so we can monitor the seeing quality at the site. We also have cameras on the towers now, and you can go to our webpage and we have a near real-time feed from the video camera. In fact, this is a frame from the camera that you can watch on the webpage. This is a recent drone video, bird's eye view of the summit. So again, you can see the excavation for the foundations of the pier and the enclosure, our temporary office building. This is the area on the opposite side for a future large telescope. And we're going to use this area as a concrete batch plant for when we pour the concrete foundations. This is the building where our workers reside. We can house about 200 construction workers on the site at any given time. We've had surprisingly large construction crews for the work that we've done to date, so we're a little bit concerned about running out of space on the summit. So we're investigating what we can do to get some additional accommodation. And then I'll end here and answer questions. There was an eclipse recently in Chile, and the interesting part is that in blue here I've plotted the eclipse path, and this red marker just outside the path of totality is the location of our construction site. So we were just outside the eclipse path, but we could drive down the access road to this yellow star and be in the eclipse path. So we organized together with the Carnegie Institution, erected a huge tent. We had a huge party down there and invited lots of wealthy people who might be doctors. And of course, you never know what kind of weather you're going to get, but we had beautiful conditions for this eclipse, and I took a couple of photographs. I'll just show you a couple of them. The sun was not very active, so there were no sunspots visible. There were very few prominences on the limb. And it wasn't a particularly long eclipse, but it was beautiful conditions. So you can follow us on social media. We're on YouTube, Facebook, Instagram, etc., and Twitter. And I encourage you to follow along. And I think I'll stop at this point. Thank you for your patience, and I'll take any questions. We'll start in the front row here. If you don't mind my pointing to people, if you'd rather select them. No. Okay. I'll try to be equitable.
My question is, you must have an interest in extraterrestrial and celestial life, right? One of the interests in this project?
So the question's about extraterrestrial intelligence?
Yeah.
So what is your question?
Well, if there was such a happening, how would the team respond to that, and would they be ready for it? I mean, what do they have set up for that if that happens?
So I have to say we do not have a contingency plan in the event that we discover intelligence in the universe.
Okay.
Perhaps we should develop a contingency plan. Personally, I my own personal belief is that the universe is vast. And if we were the only life in the universe, it would be a tremendous waste of space. So I have to believe that there's something out there. I know that there are some people, I think Stephen Hawking was one of them, who felt that we ought to be worried about contact with extraterrestrial intelligence because we might be on their menu. But, so to be honest with you, I don't know what my contingency or reaction would be. I would be astonished and I think pleased to discover intelligence elsewhere. Yes, sir.
2 questions. You didn't mention first light. When do you expect the scope to be up and running?
So first light, our plan for first light, which would be the first use of the telescope for imaging heavens, we intend to let me say that our schedule is such that we anticipate having 4 mirror segments finished and on the mountain by the time that we take delivery of the telescope mount and enclosures ready to receive the telescope mount. So we envision putting the first 4 segments in and calling that first light and doing what we would call shared risk science with the telescope configuration. And the date for that is dependent on several things, including the rate of fundraising and the rate at which we can make technical progress. So at the present time, I would say it would be in the mid to late 2020s. I'm not going to give you a particular date because it's dependent on different factors.
Second question, will it ever be possible to visit this site as a non-investigator?
So the question, can you visit the site as a non-investigator? I would say certainly we'll make arrangements for tours of the facility. I should also mention that in the last year, there has been quite an interest by the National Science Foundation in becoming partners of both the Giant Magellan Telescope and the 30-meter telescope. And I think the interest of the NSF would be in providing the U.S. science community as a whole, in large, access to the leading instruments, the leading telescopes in the next era going forward. So should the National Science Foundation become involved, then there would be, I think, much more general access for the U.S. astronomy community, and perhaps even amateurs could write proposals to get time on the telescope. But we do envision being able to support a degree of visitation of the site. In fact, at the Eclipse event, I think we toured about 350 people, visitors across the construction site. Yes, sir.
At the bottom of all your slides, I see it says MAS briefing. What does the MAS stand for?
That stands for the Milwaukee Astronomical Society.
Excellent.
Oh, shit.
So kind of like where you started and where you are.
Yes,
That's come full
back to
circle.
my origins.
Oh, shit.
In the telescope business. So can we go to this side and then back over to this side? Yes, sir.
Do the adaptive optics ever cause issues with fatigue in the glass surfaces? And do you ever see breakage or have to know what you would do if something like that were to come? Or is the motion so incredibly small?
Yeah, so the question is, these adaptive secondary mirrors that have a thin face sheet, do they ever suffer fatigue? And the answer to that is that the motions are so small that the glass, in this case it's actually zero that's used for these face sheets, is well within its elastic limit, so there's been no damage from that. But I will say that the earliest couple generations of these mirrors have had some reliability issues. They're very complex machines. They have to be cooled to remove heat. The functioning of the actuators and so on has been a learning experience. So there have been some teething issues with the mirrors, but by now they're actually quite reliable. They're used every night on a large binocular telescope, and we think by the time of the 4th generation mirrors we will use that all the kinks will be ironed out, and we won't have serious operational issues with them. That's our expectation. Yes, sir.
This is definitely not your father's telescope, right?
No, it's not my father's telescope.
Well, yeah, this is definitely a very high-tech telescope. when you're doing the spin casting, those make a parabolic surface, which would be fine for an on-axis mirror. How? So you spin all the mirrors in the same way, and you get this perfect parabola. But for the off-axis mirrors, you have to grind those specifically to be off-axis, so that's where the grinding comes in.
Right, so the question is about the manufacture of these spin cast mirrors, and by spinning them in the furnace when they're still in a molten state, we develop a parabolic surface from the centrifugal force. Of course, the off-axis mirrors need a different figure than an on-axis parabola that you get from the casting process. But the idea is that the concave surface gets you very far along in terms of reaching the final figure that you want. Yes, there's additional polishing, and when we finish casting the segment, the top plate, the thickness of the glass on the front surface of the mirror is I think about 3 inches thick. We grind that down to a couple of inches, so there's still quite a bit of material removed in the grinding and polishing process, essentially all in the grinding process. And so you have to grind in the off-axis figure. But the parabolic figure that you start with takes you a long way towards achieving that final surface.
You know, just between, since it's just us here in this room in MAS, is there a possibility you really want to share with us that this shifting design of the pins and for the earthquake was actually came in the sleep one night, remembering how many beer bottles you threw down on the bottom of our telescope over here and all that?
Yeah, so the question is relating our current peer design. That's what we did for the Z-scope. So I don't actually remember how many beer bottles went into it.
And then what would handle an earthquake here if we had? There's enough.
If there were seismic events in Wisconsin, I probably would give you a little bit of protection. Not much. Yeah, let's be fair to the back of the room. Who have I missed in the back? Anybody in the back? Okay, coming forward. Yes, sir.
Spare parts, including mirrors and electronic components over a period of 50 years. Any thoughts on that?
Yeah, so the spares policy is an interesting question. What we are doing is having each of our suppliers recommend the spares that should be on hand, and we have defined, I think I mentioned a couple of different levels of earthquake. There's a level of earthquake that we just want to be able to effectively operate through, so there's no impact. We'll have our observations interrupted during the earthquake, but we can resume operations immediately afterward. Then to a more severe level earthquake where we've specified that we want to be able to return the observatory to operation in a reasonable amount of time with available spares. And so we're leaving a bit of judgment there for what it means. So we've decided not to have fully assembled spare hardware, but we will have sub-assemblies and other components, particularly long lead components, available so that we can do repairs after an earthquake. We have a concept for an 8th mirror segment that I would call an operational spare. So it would be an off-axis segment. It would be a 7th off-axis segment. And the idea there is that we want to recoat the mirrors periodically to refresh the reflective surfaces. So it would be convenient for us if we had an additional off-axis segment that we could take our time putting through the recoating process, and then during an engineering day shift, we could swap it out for one of the segments that's on the telescope, and then take that segment off and coat it in our leisure.
How often would that occur?
So the question of how often would we have to recoat is an interesting question, and we don't have a crisp answer. It depends in part on how clean we keep the mirrors, and in part how durable the coatings are on the mirrors. So right now we're expecting that we will do CO2 snow cleaning of the mirrors every day, and we have actually made provision in the specifications that we could do wet washing of the mirrors, there'll be a drainage method to take the cleaning soap off the surface. So if we can keep the mirrors very clean, then the interval with which we'd have to recoat them would be stretched out. There has been a suggestion of mirror Roombas that would run around the mirrors. I'm not sure how practical that is.
What are you going to coat the mirrors with?
So just to tie off this question, we're planning nominally to recoat the mirrors every couple of years, each of the segments. And the concept right now is that we would coat the primary mirrors with aluminum. Perhaps we would use protected silver at the secondary mirror. But we would like the flexibility to be able to move to different types of coating in the future. So we've specified the coating facility, which is a magnetron sputtering coating approach in our current concept, to have the flexibility to deposit different kinds of reflective surfaces and overcoats.
So for starters, you're going to use aluminum.
So for starters, the point is to use aluminum. Okay, let's go to the center of the room here.
What are the energy requirements of this complex and how are they met? Is there commercial power available?
So electrical power. So one thing that's interesting about Chile is that it's really a very progressive nation. It's the fastest growing economy in South America, and they just have an explosive growth of renewable electrical energy source in the country. So we actually hired a firm in Chile that specializes in advising you on what your options are for obtaining electricity. So the electricity on the site at the moment comes from the grid in Chile. It comes from a line that goes down the Pan American Highway. And we anticipate that we're going to have new infrastructure for operational power. We plan to build a 5 megawatt electrical power capacity. Will probably consume about half that amount during operations. But we expect that we will likely contract for electrical services, and that service provider will capitalize any of the infrastructure that's necessary to route that power to our site. There were other questions. Yes, sir.
I thought the two Keck telescopes in Hawaii were sort of, or could be connected in an interferometer type connection. Would at some time in the far future this telescope maybe be connected to the other observatories in Chile to make a really giant?
Yeah. So the question is about interferometrically connecting telescopes. So I was the project manager of the Keck interferometer. So I brought the Keck interferometer. I was project manager and I brought it online. So in that case, we connected the two 10-meter telescopes together in a complex set of optics underneath the observatory. There was another experiment that was run between Keck and the CFHT telescope on Mauna Kea, where they ran a fiber to couple the two telescopes, and that was also very successful. So we have had discussions about how we might connect this telescope either to a second giant telescope on the same site adjacent to us, or potentially even to other observatories. I think the feeling at this point is that such interferometers in the future are likely to be fiber coupled, and so that gives you a lot of flexibility in what you can do. So we're not doing anything specific in the design of GMT at the moment, but we have had discussions about the potentiality of connecting telescopes.
Would it have been cheaper if you separated out the 7 mirrors, out a little ways, and then made an interferometer on the same mountaintop, or than this, like putting them all on one mount or not?
Yeah, so the question is about separating the mirrors out. I would say that is a technology step that would be a bridge too far for us at the moment. I think we have our hands full with the technical challenges that we're overcoming for GMT. So perhaps in the future one can contemplate that. This is a much easier job to do in the radio wavelengths where you can do demodulation and like the event horizon people image the black hole. That's a harder problem than the optical. Yes, sir.
I'm interested in your adaptive acoustic adjustments that you're doing. What's your computational rate to be able to do the 5,000 actuators at a 1 millisecond adjustment? In terms of how much data are you passing through and processing to be able to do it that accurately?
Right, so this question has to do with the computational power needed to drive the adaptive optics of the secondary mirror. I don't have numbers at hand. I can probably, if you give me your email address, I can probably point you to some journal papers that discuss this. one of the issues that we have to pay attention to is the latency in the calculations to minimize the time delay in the control loops, which can be a limiting factor for bandwidth. So we actually intend to have computational engines that are fairly close by the secondary mirrors, so we can minimize those kinds of delays. But I don't have a crisp answer for you. Yes, sir.
In your introduction, you touched on some likely observations that you'll be making. You talked about searching for planets and features of the planets that might indicate life. Can you give a couple of other examples? Can we expect a series of Hubble-like gee-whiz photos coming from this?
So in terms of initial observations or sort of key science, we are building an imaging camera, as I mentioned, because it's really hard to describe to the public what you're doing when you're taking spectra. It makes for a much more impressive press release when you have an image like you get from Hubble. So we will have the ability to do imaging on the telescope. But right now, so back up and say every 10 years, there's a process that's undertaken by the U.S. government called the Decadal Survey. The National Academy of Sciences conducts a decadal survey, and panel a number of scientific experts, and they basically look ahead for the next decade at what the scientific priorities should be for the government, essentially for NASA and for the National Science Foundation. And there's a decadal survey in astronomy and a decadal survey in some other areas. So the decadal survey for astronomy just got kicked off recently. Panels have now been announced. So for the next year and a half to 2 years, there's going to be a process to determine what the scientific priority should be for the United States. And as a part of that process, early on, there are white papers that are solicited from the science community on what kind of science does the community envision being critical to answer the burning questions of the era in the next decade. So those white papers are now being submitted, or have been submitted to the Decadal Survey, and that's really, I think, where we're going to get the best understanding of what observations are really going to be needed in the next decade. And of course, there are going to be discoveries of things that we don't know how to predict at this point or ask for. But certainly among the measurements we'll be making are extrasolar planets. We have the ability with this telescope to actually image the planet orbiting Proxima Centauri in the southern hemisphere. We will be able, of course, to image galaxies very early on in the universe with a degree of spatial resolution that we don't have today. We'll be able to probe in areas of dark energy and dark matter. So I would point you to the Decadal Survey white papers, I believe which will all be publicly available, and to go into our science book to get an idea of what some of the key observations will be. Yes, sir.
What were some of the limitations that had to be overcome to get this size, and do you think that doubling every 30 years rate is sustainable?
So the question about the growth of size of telescopes, I would have thought that going beyond a 25 or 30 meter telescope would be nigh on impossible. But I just finished reading the book by Ronald Florence called The Perfect Machine, which recounts the story of the building of the 200-inch Palomar telescope in the 1930s and 40s. They didn't finish it until after the war. I think if those people were to look at what we were doing today, they would just be astonished at what we're doing today. And so I don't want to say that trend will not continue. That there won't be a 50 or 75 meter telescope contemplated in construction 30 years from now. But in terms of some of the challenges we have, there's just a limit to the size of mirror that you can make. Even underneath the football stadium, there's only so much space. So once you start segmenting mirrors, like they did with Keck, now you have a number of technical challenges. How do you phase those mirrors? How do you align them? How do you control them? And so part of the challenge we have is we have large mirrors, which are not zero expansion material, which have significant gaps between them, and we need to phase across those gaps. And we have a doubly segmented optical system. So that's one entire realm of technical challenges, is how we're going to accomplish that phasing and control. And another realm that's proving to be a challenge is how do we protect a telescope of this size against a massive earthquake in Chile. So say those are the main technical challenges in just going to this scale. Yes, sir.
Been an uproar recently about like SpaceX and all the constellations and satellites that are going up, and even Chile in remote areas that wouldn't be affected by all those satellites. Is there anything from like an engineering standpoint you can minimize the effect of those reflections? Even with spectroscopy, I would think that might have an effect.
Yeah, so this question is about the relatively recent discovery that there are some business models from Elon Musk and others that would involve orbiting tens of thousands of satellites in the low orbit. And of course, during certain times of the day, these things are very visible from the ground. And there is concern that's been expressed by the American Astronomical Society about the unregulated proliferation of satellites in orbit and what it might do to astronomy. I think there's an equal concern in the radio domain that if they're emitting electromagnetic radiation, it will affect potentially radio astronomy. So I'd say that there is concern about this. There are obviously things that you can do to break up observations and just throw away the data is corrupted by the presence of the bright object. But it's an area of concern. Excuse me, are there any other questions? Yes, sir.
What happens if one of the mirrors of the 7 mirrors becomes defective, or like say cracked, or how does that interfere with the whole process?
So the question is, what do we do in the presence of a cracked mirror? So I would say it would depend on how great the damage is. So it's conceivable that we could return the mirror and repair it in the mirror lab. Excuse me. It's conceivable we would have to replace the mirror, and that would be a big job, replacing the entire mirror.
And what's the final cost of this whole thing, and the continuation cost?
So I'm really not at liberty to talk about cost estimates. I would say that it's more than $1 billion to build it, but less than $2 billion. Our looking at the operation costs of a number of different ground-based observatories, our conclusion is that the yearly operation cost is typically on the order of 3 or 4 or 5% of the capital cost. So that would be a rule of thumb that I would use for operations expense. Yes, sir.
How the mirrors will be moved to the side? How will they be moved to the
How
side?
will the mirrors get to the site? Yes, so this is an interesting question. My preference would be for a heavy lift Zeppelin to show up at the mirror lab and pick the mirrors up right out of the parking lot and then deliver them to the mountain directly. I know there are people working on heavy lift Zeppelins, but there isn't really a commercial service available to do that kind of a job. We've looked at fitting them into a C5 Galaxy, and the mirror cells are a little bit too large to go into a C5 Galaxy. So likely what we will do is what the LSST project just did with their 8-meter mirror, and that is we put them on special shipping through the Panama Canal to one of the ports in Chile, like Coquimbo or farther up the coast, and then we'll truck them over the Pan American Highway and up the mountain. So we improved the access road to Las Campanas so that the bend radius of the roads and so on could accommodate the transport of the largest components that we could imagine for the observatory. So my guess is that they will go by sea and then by truck. LSSD has a challenge in that they have to go through a tunnel. And so they actually work with the people designing and building the tunnel to make sure the tunnel is wide enough that they can take a 28-foot in the air through the tunnel. I think there was like just an inch to spare. Yes, sir.
How sensitive to failure is the scope? If one of those mirrors cracked, is the whole scope out of business until you get a replacement, or could you work around one of them failing?
So the question is, can we still operate without one of the segments? And the answer is, of course, you could still operate, but you would lose that light collecting area, and you would wind up with a somewhat strange-looking point spread function with part of the pupil missing. But in principle, you can mask out that area and continue to operate. And indeed, we're going to operate in the first light with 4 segments, probably the center segment and then 3 of the 6 outer segments. So yes, you could operate in that way. No question about it. Yes, sir.
Just one more question. That you made in the mirrors, you showed all the glass pieces being put out there. How do you keep the air bubbles out of that once you melt it? Do you shake it or something, or how do you get the air bubbles?
Yes, so the question is, how do we get the air bubbles out? So inclusions of air bubbles has been a really serious problem, going all the way back to the 100-inch, I guess even this was the 60-inch. There was a particular problem with the 100-inch. When you could look at the 100-inch telescope, you could look at the mirror cell through the back, and you look at the mirror blank, and it's just full of air bubbles. And when they took delivery of the mirror blank for the 100-inch from the glassworks in Paris, they basically thought it was hopeless. But then they discovered that they actually could polish the front surface without getting to the air bubbles. So air bubbles in mirrors has been a huge issue all along. But what's remarkable about these mirrors is that when you look at the video, you can see bubbles coming up to the surface. So I think it may be due to just the temperature, the viscosity of the glass that it's held in. Maybe partly it's the spinning of the furnace. But there are very, very few inclusions of air bubbles. There are a few, but they're small and there aren't very many of them. Yes.
Jim, you gave a timeline about when this thing is going to be done. And with your job in here, I'm just going to ask you a personal question. Do you expect this to be your last job?
I would be okay with this being my last job. Our current schedule shows we could be finished with construction as soon as 2028. Again, depending on many other things going well. But it's not quite as long as building a cathedral or the medieval. But you do have to take the long view. And,
you need an equal number of prayers then?
We hopefully don't need any miracles. We try to avoid the need for miracles. Yes, sir, at the back.
I was just wondering, say around 2028 or thereabouts, do you think you could invite your friends of MES?
Well, I'll make a deal with you. If we're finished at that time, I will certainly extend a broad invitation to the MES to come out. We can charter a couple of buses and come out.
My membership will be in the mail tomorrow.
Yes, sir.
The sources of revenue for this return on investment and that type of thing, is that something that you think about, or is it all scientific and nonprofit?
So I'm not part of the development arm of GMTO. The deal I struck when I became project manager is that they would raise the money and I would spend it. Kind of a deal that I like. But seriously for a moment, as I mentioned at the outset, the scientific institutions that form a collaboration for GMT have been providing the funding in return for access to the world's largest telescope. If you're a scientific institution and you want to be doing science at the cutting edge, if you want to hire and retain the best faculty, you have to provide them with access to the best data. And so that's at the core of the motivation for institutions to contribute to projects of this kind. And indeed, I mentioned that the National Science Foundation has expressed an interest in the broader U.S. community in having access. There are also, just philanthropists out there, individuals of high net worth that are interested in contributing to noble causes, and so we've actually had significant contributions from individual philanthropists. So the source of funding, I think, is as diverse as it needs to be for a project on this scale.
However, it is somewhat, things can be lean because indeed it has affected Yerkes here in Wisconsin, the funding for GMT, is that correct?
So I don't know of any direct linkage between GMT and the University of Chicago's decision on Yerkes. I think the situation at Yerkes was a long time process. It's a very beautiful but a very old and expensive facility to maintain. So I don't have really any insight into the decision-making process there. It is a beautiful place to visit, and I look forward to it being open to the public in the future.
How do you protect against lightning and their potential?
How do we protect against lightning?
How do you protect against lightning?
So lightning strikes are protected in the old-fashioned way first suggested by Benjamin Franklin. So we have lightning rods and arresters and grounding straps and so on.
So there's no danger?
Well, I wouldn't say that there's no danger. There's always some danger, right? You get a very large electromagnetic pulse, but what you try to do is ground things appropriately and design them in such a way that they're not overly susceptible to damage from those kinds of environments. So we've actually there is literature on the subject from the experience of other observatories. We actually did have a lightning strike on one of our instrumentation. It was measuring the atmospheric properties at the site. So we are experiencing firsthand and suffering some damage from lightning strikes. But part of the function of the enclosure is to protect the telescope from that environment as well. Yes, sir.
When the telescope is up and running, how many people will actually be at the site? Will it just be like technical people to change the instruments around or whatever, and the astronomers will be on their computer in their home office someplace, or how will it work?
Yeah, so the question is, what is the nature and makeup of the staff that will be on site during operations? And we're actually building now the operations model for the observatory. And the majority of people who will be on the site are the people who have to maintain and do engineering on the telescope during the day shift. I would imagine that the majority of astronomers and those using the observatory at night for scientific investigation will not physically be at the mountaintop. They will be remote observing, either from a facility in La Serena or from other sites in the United States, or indeed from their smartphone. So we're actually working now on the design of the control room and trying to better understand what kind of remote and telepresence capabilities we would need to support scientific observing. But we would expect that there would be 2 or 3 dozen or even more people on site to do engineering during the day shift. It's a large and complex machine. It will require a significant amount of care and feeding during the day shift. Have I exhausted all questions?
I have one quick one.
Yes, ma'am.
Kind of personal. Do you ever get any sleep?
The answer is yes, I do get sleep, but probably not enough.
Okay. Yeah.
All right, so I don't want to trespass on your time any further. Thank you very much. Right. You get your gear? Thank you very much.
I hate to run. My wife works third shift. Thank you very much for this. This is absolutely my pleasure.
I know, exactly.
Constant monitoring and then retrospectively adjusting for extreme sound and tissue and the body. So see the light camera hang on the tissue. So that's why I trust around.
Very good.
Yeah, that's good.
Yes, so we have papers on that.
Is it off of the website, the GMT?
It may or may not be.
Who's your next big speaker coming out?
Working on it.
John asked Liz.
No, I was just looking to see if you had one here.
Is he still in Colorado?
Oh, yeah. Yeah, I'm in contact with him multiple times a week. He comes and visits almost annually, so.
So John was doing some work at the Jet Propulsion Laboratory when I was there.
Yes, he
Oh,
was.
yeah, the flash is good. Yeah, so.
Yeah, he was. He
So
told me.
on my camera, probably
That's
that's
kind
kind
of
of
neat.
Yeah, it's basically this.
Yeah, he is.
On the face.
They're not up to much right now, but having trouble getting contracts. He just turned 69, so I don't know how much longer he wants